Hi, as part of this week's review videos, today I'm going to be talking about MSTs in graphs and how to find them using two different algorithms, prims and Kruskal's. I'm also going to briefly touch on why MSTs are useful in the real world and differences between prims and Kruskal's and when you would want to use one over the other, because they both really exist for the same purpose of finding an MST within a graph. So starting with the basics, what is an MST? Well, it stands for minimum spanning tree. As you'll remember, a tree within a graph is just any sort of subset that doesn't have a cycle, and a spanning tree is a tree that contains every node of the graph. So you want to include every node, but without having a cycle anywhere in that subset. And then, as you can imagine, a minimum spanning tree is a spanning tree that minimizes the total cost of the graph or of that spanning tree. So for this example, this graph starts like this, and then would be the spanning tree based on that graph. You'll see every node is there, 1, 2, 3, 4, 5, and 6. And we've eliminated some of the higher cost edges, such as the 15 and the 14. Now, a key distinction between MSTs and SPTs from a couple weeks ago is that SPTs have to do with starting from one certain source node. So you're saying starting from, in this instance, A, what's the cheapest way to get to B from A? And also, what's the cheapest way to get to D from A? And so on and so forth. It doesn't look at the graph as a whole. It's not meant to be minimizing the total cost of graph. It's minimizing the total cost from node A. Whereas an MST looks at the graph as a whole and minimizes cost along the entire graph or in the whole big picture. So if you'll sum up the edge weights for that SPT, you'll actually see that it's a total cost of 7, while in this MST is a total cost of 6. So an SPT can sometimes be misleading. An SPT is not always an MST. And MSTs are actually really useful in real life, even if it doesn't always look like it. Basically, this notion of finding every single item and minimizing the cost to every single item is really, really useful for creating a network of something. For example, a network of computers, where you can say, oh, going from this computer to that computer is slower than going from this other computer to that computer. So if you're saying, I want to include every single device in my network, but I want to do it in the most efficient way possible, let's say if I wanted to transfer data from one device to another, you would use that MST and you create that MST to figure out what path you want to take to, transfer data or something. Along the same line of thought is circuit design. If you say, hey, I wanted to include every single item or every single device in my circuit board, but I want to do that using or minimizing the amount of wires I have to use, then you would want to maybe make an MST to do that. It can also be applied to some machine learning and data science concepts, grouping and clustering data, as well as image tracking, like tracking your face on a camera, and handwriting recognition also uses MSTs in some way. If you want to read more about that or more about them in general, I've put a couple links here, or you could just do some research on your own. It's pretty fascinating. But the point is, MSTs are really, really useful in real life, and that's why there are so many algorithms devoted to finding them within a graph. We're just talking about two in this class. The first one we're going to talk about is Prim's algorithm. Now, how this works is we're going to start from a certain source vertex, and then on each iteration, we mark that one as processed, and we see where all it could go to next. And then we mark down where it could go to next along with its distance and the edge to go to that one. And you could include candidates from your previous iteration. But basically, you want to, out of all your candidates that you could go to next, you want to then go to that closest one, that shortest one with the smallest edge weight. And that edge that you've just traveled along would be part of your MST. As a side note, when you're going on a next iteration, if you come across a vertex that you've seen before, but the new edge weight to that vertex is better than the other one you saw, you can overwrite it and say, hey, we don't need to look at that other one yet. We could instead do this one because that's a better way to reach that vertex. And on the same token, if you found a new edge to a vertex that's worse, or if you found a vertex that's already been processed, at that point in your algorithm, you can just ignore that edge. If you're a person that thinks in terms of pseudocode, here's that for you. You can always refer to this later if you want to code it up, but this is pretty good pseudocode for this algorithm. So in this example, using this graph, which I'll also use for Kruskal's, my Kruskal's example, we're going to be starting at A as our source. So we mark A's distance as 0, and to start, we mark everything else as infinity distance. And we'll say that the best edge to A is nothing because we're not going to A from somewhere. We're going to be starting at A and going somewhere else. So to start with, we say A is processed, and then we look at where all it could go. It could go to B, and it could actually go to B in two different ways, but obviously we want to take the cheaper of those two ways. So we could say it could go to B with distance 6, and that would be this edge that we mark down here. It could go to C with distance 3, and it could go to S with distance 7. So those are our next three possible candidates. We haven't yet encountered nodes D or T, so those are still distance infinity. So now out of our options that we could go to, the cheapest one is going to C. So we'll note that A to C is part of our minimum spanning tree, and now we're at node C. So we mark that as processed, and then we look at its possible next candidates. It could actually go back to itself using this edge, but we can have like a logic in our code that says if we're traveling to the same vertex, then obviously don't include that because that would create a cycle. But basically we're not going to include that. It could go to S, but that's with distance 8, which is worse than the option we already had. So we don't include that. It could go to B with distance of 4, which is better than the option we had earlier, this A to B with distance 6. So we change that. Now the best way to get to B is distance 4 that we currently know of. And also we've been introduced to node D, and C to D is of distance 3. So now those are our next three options, either B, D, or S. Of those three options, the cheapest one is going from C to D, so we mark that as part of our MST. And then once again, we'll start with D, mark it as processed, and look at its next possible candidates. The only two next places it could go are to B or to T. But it turns out both of those are very important because going from D to B is again a cheaper option to get to B. So we change that in our table. And we've now been introduced to node T. So going from D to T is the cheapest way to get to T as we know of. So we mark those two down. And at this point, we have a tie going from either D to B or D to T because both have a distance of 2. Both of those edges have a distance of 2. At this point, it's really up to your algorithm as to how it breaks ties. But I'm just going to go D to B first. I don't know, maybe by alphabetical order, but that's the one I'm going to look at next. So D to B, we mark node B as processed, and now we look at the next possible candidates for B. It could go back to A in those two different ways, but A is already processed, so we don't want to include those edges because that would create a cycle. We could go back to C, but again, C has already been processed, so we don't include that. Or we could go to T, but that way to get to T is actually more expensive than the way we had earlier from D to T. So we don't do anything at this node. We just mark it as processed, and then we move on. The next cheapest option would be this D to T edge. So we go along there, include that in our MST, and mark T as processed. And the only place that T could go at this point is to B, but B has already been processed, and we don't want to make a cycle, so we don't do anything at node T. And then the last step would be to traverse to the last node that we haven't put in our MST yet, which is this A to S link. So we mark that as part of our MST, we mark S as processed, and now every node has been processed. So we found our MST. It's done. So that's how prims works. As you'll notice, it's kind of similar to Dijkstra's in some way. You will need a priority queue to sort of mark or to keep track of what's your best option at each point, but it's a little bit different. So the next algorithm we're going to be looking at is Kruskal's algorithm. And rather than looking at vertices and looking at how to get from one vertex to another, or starting with a certain source vertex, Kruskal's works more in terms of edges. So the first step we do is to sort all edges by weight. And we want to sort it ascending so we can pull the minimum one at each point. And we're actually going to look at edges and the vertices that they happen to connect rather than looking at vertices, sorry. So we're going to pull the minimum edge at each point is how that algorithm is going to work. That's why it's working in terms of edges. So before we do that, we want to put each vertex in its own set using our disjoint sets ADT. And at certain points, we're going to merge vertices to let our algorithm know that, hey, at this point, these two are in a certain set, and that's one part of our MST. And the disjoint sets ADT actually makes this much faster than any other implementation of this algorithm would. So if you weren't convinced that disjoint sets can be useful in practice, here you go. So you start each vertex in its own independent set. And then, like I said, the first step you want to do is pull the smallest edge, and then seeing the two vertices that that edge connects, you merge them into now one set. And then you keep repeating this process. You'll pull the smallest edge and then merge the two vertices that edge connects, but only merge if that would not create a cycle. So you don't want to merge if it would create a cycle. And the way you would know if it creates a cycle is if the two vertices that edge connects are already in the same set. If they are already in the same set, then including that edge would make a cycle. So you would ignore that edge. So you only want to include an edge in your MST and merge if those two vertices are in separate independent sets. And a sort of high-level pseudocode for crusticles is here using the disjoint sets algorithm, or sorry, disjoint sets ADT. This is kind of more of a basic pseudocode as compared to the prims one, but here it is for future reference. And using the same graph as earlier from prims, we're going to run this algorithm instead and see how it differs. So pretend that we've already sorted all the edges in a collection somehow. We've already sorted it. And the first step we're going to do after putting each vertex in its own independent set is to pull the smallest edge. And the smallest edge in the graph actually is this self edge going from C to C. So we're going to look at that, but obviously going from C to itself would create a cycle. So we don't want to include that. The next one, like I said, there's a tie here. So again, it depends on how your algorithm breaks ties. But I'm going to look at this B to D edge first. We know that B and D are in their complete independent sets because that's how everything starts. So we can safely merge those two and say that that edge is part of our MST. The next cheapest edge we could look at is D to T. Now, D and B are in one set, but T is in its own set. T is not already in that set with those two, so we can merge that no problem. The next cheapest edge to look at is A to C. A and C are in their complete own sets, so we can merge that no problem. And then we look at this edge also of weight 3 between C and D. Now at this point, A and C are in their own set, and B, D, and T are in their own set, but there's no overlap between those two sets. So we can actually merge this without creating a cycle. So the next one we look at is B to C, but it so happens that because of these two edges, C to D and B to D, that means that B and C are already in the same set. So adding this edge would create a cycle. So we don't add that edge. The next one is B to T, but again, obviously that would create a cycle. We don't include that. A to B would create a cycle because they're in the same set. And then now we look at A to S. At this point, A, B, C, D, and T are in one set, but S is in its own set. So since there's no overlap, we can merge that successfully. And for the sake of illustrating the algorithm, we could do the last two and say, hey, these two would create a cycle, don't include that. These two would create a cycle, don't include that. But you would really want your algorithm to stop at this point now that you've included every single node in the cheapest way possible. So once you've included everything, you're really probably done. So you would want to have a stop condition in your code that increases efficiency. And this is the MST that we came up with. And as you remember from the prims algorithm, it's actually the same one. So that brings me to a question. Based on a certain graph, is the MST of that graph always going to be unique? is there always one MST to one graph? Well, it kind of depends on if there's duplicate weights at certain positions. And as we saw, there is a duplicate weight. B to D and D to T are both of weight 2, but that didn't end up affecting things. However, if the weight from B to T was 2 and not 5, then that would make 2 possible MSTs for the same graph. We could do this way on the left or this way on the right. And then that would depend, which one your algorithm finds would depend on how, again, it breaks ties and how it works. But that goes to show that one graph doesn't necessarily have one MST. It really depends on whether you have certain duplicates of edge weights. And lastly, I'm going to be discussing the difference between prims and Kruskal's. So as I said earlier, prims thinks in terms of vertices, while Kruskal's thinks in terms of edges. They work a little bit differently too. Prims builds up one connected tree, while Kruskal's builds many sort of smaller sets, smaller trees, and combines them into one. And prims, because it works with vertices and not edges, works better with dense graphs, while Kruskal's works better with sparse graphs. And here's an example of each of those. Based on what we know about these algorithms, you can understand why Kruskal's would be slower for that dense graph. You would have to look at a lot of edges that maybe you would not need to look at, while prims would be a little bit faster on that type of graph. And on that sparse graph on the right, prims wouldn't necessarily be slow for it, but Kruskal's would be a better way of solving it. So thinking about which one you would want to use over the other, it really depends on what you know about your data. So if you know your data is going to create a dense graph like the one on the left, you would want to use Prim's algorithm. So it depends on what you know about your data and how your data is, or how your graph is going to be made depending on your data.